In this video, I'm going to show you how to use transformations now to graph log functions. I'll assume you have a basic understanding of transformations and that you have a basic understanding of what I call parent log functions, standard log functions with no transformations. Okay. Alright, so let's get started with our first example. Let's see. Graph using transformations. And let's say the function we want to graph is f of x equals log base 3 of negative x minus 1. Okay? So the first thing we need to do is identify the parent function. And the parent function here is some log of x, and in this case it's log base 3. So the parent function is y equals log base 3 of just x. Everything else is a transformation. So this negative and this minus 1 are both transformations. Okay? So we'll come back to the transformation shortly though. First thing we need to do is get a graph of y equals log base 3 of x. So I'll put in some x values and calculate the y values. And in this case, the x values we want to use, since this is log base 3, we want to use powers of 3. Okay? Those are easy to calculate. So 3 to the first is 3, 3 to the second is 9, 3 to the third is 27. We could keep going. In fact, 27 is probably too big, so I won't actually use that. 3 to the 0 is 1, 3 to the negative 1 is 1/3, 3 to the negative 2 is 1/9, etc., etc., etc. And so you see that you kind of get the powers of 3 that you're used to, 3, 9, 27, and then you get their reciprocals here also. And in the middle you get 1, okay? So that's our parent function. Those are our ordered pairs. Now we need to calculate the log base 3 of each of those x values. So I always like to start with 1, log base 3 of 1, because x is 1, and y is log base 3 of x. That's 0. Log base 3 of 3 is 1. Log base 3 of 9 is 2. Log base 3 of 1/3, since I get a reciprocal, that's negative 1. And log base 3 of a ninth is negative 2. Okay? So if we plot those, 1, 0 is right here. 3, 1 is maybe like right here. 9, 2 is over here. So to the right, our graph is flattening out. Then I need to plot 1/3, negative 1. So I go right 1/3, and I go down 1. And I go 1/9, negative 2. And you keep getting closer to the y-axis here. So this is our parent function with an asymptote on the y-axis. So I like to list that as part of my ordered pairs over here. The asymptote is the equation x equals 0 because it goes to the x-axis at 0. It's just a vertical line. Okay, so good, we've got our parent function set up. This is our starting graph. This is the only graph we actually calculate anything, okay, based on a function. Now we do everything else based on transformation. So I look for my x transformations. X transformations happen where x lives, and in this case, that's the inside the log. This is called the argument. So I need to take negative x, and to get x transformations, I treat that negative x like it's in an equation that I'm trying to solve for x. I want to get x by itself. And to get x by itself, I would divide both sides by negative 1, and at that point I'd have x by itself. Now the x transformation is what is the steps I did to get x by itself. So in this case, it's divide by negative 1. So I'll say divide x, because it's an x transformation, by negative 1. So that's my one x transformation. Y transformations happen outside of the x part, so outside of the log. So that's the minus 1. And y transformations are simple. They're just what you see. So my y transformation is subtract 1. And since it's a y transformation, I'll say subtract 1 from y. Okay? So I apply these transformations to this stuff here, this graph, these ordered pairs, this asymptote. The asymptote is going to be affected by x transformations only, since it's an x equation. Affected only by x transformations. Okay? That's because it's an x equation. Alright, so it doesn't matter which of these you do first. Let's divide x by -1. So I need to go in and divide each of these x values by -1. And when you divide x values by -1, they're all going to become negative, so the whole graph's going to flip over the y-axis. So let's make our new list of ordered pairs. I'll do that below. And all my x values are now negative. And in fact, when I divide x by -1, I also need to write in divide by -1 on this 0 because it's an x value. However, it does not change. So my asymptote doesn't change. I mean, I applied the transformation to it, but it didn't change my asymptote. Okay? So now let's plot those points and see what happens. I always like to track the one in the middle here first. -1, 0 is now over here. My asymptote is right here. And if you plot the rest of the points, you'll see that your graph does this kind of thing. Flattens out as it moves to the left now. And approaches the asymptote from the left as well. Okay, so I'm not being terribly precise here, just giving you the idea that these ordered pairs give you this graph. And the reason for that is the graph flipped over the y-axis when the x values all became negative. Now I need to subtract 1 from my y values in this table. So I'll write -1 next to each of those y values. Okay, and it does not affect my asymptote. So now I'll list my new order pairs and we'll do it again. And when I subtract 1 from my y values, it's simply going to move my graph down 1 unit. Okay, so let's plot those points that I've got here. My asymptote stays where it was before, so let's draw that in. That's my boundary that I get close to. I've got -1, -1, so -1 was at 0 before, now it's at -1, it moved down 1. Then now I've got -3, 0. I've got -9, 1. So again, my graph is flattening out as I move to the left. It just starts 1 unit lower than it did before. Okay? Then I've got -1/3, -2. I've got -1/9, -3. So my graph is getting close to my asymptote again from the left. It just moved down 1 unit. And so this is my final graph of my function f of x equals log base 3 of -x minus 1. I started with my parent, I did both of my transformations, and I ended up with this function. Let's do one more example if I have time. In this particular transformed function, my base is 1/2, so my parent function is log base 1/2 of x. And when I set up my x, y table, my x values will be powers of 1/2. So 1/2 to the first is a half, 1/2 squared is a fourth, 1/2 cubed is an eighth. I could keep going. 1/2 to the 0 is 1, and then I need the reciprocals of these. So the reciprocal of 1/2 is 2, the reciprocal of a fourth is 4, reciprocal of an eighth is 8, and I could keep going that way. Okay, if I put in 1, log base 1/2 of the x value 1 is 0. Log base 1/2 of 1/2 is 1. Log base 1/2 of a fourth is 2, because 1/2 to the second power is a fourth. And I encourage you to pause and work through these things I'm saying here. I'm making a video to put on YouTube, which of course has a time limit, so I'm trying to get you the information you need, but you may need to pause and work it out for yourself. Log base 2 of an eighth is 3, or sorry, log base 1/2 of an eighth is 3. And then log base 1/2 of the reciprocals are just the negative values, so -1, -2, and -3. Okay? So all I did here is take log base 1/2 of each of these x values. if we plot these points, we already know the asymptote for any log parent function is, sorry I didn't draw that very well, is the y-axis, or which is referred to as the equation x equals 0. Okay? Now if I plot 1, 0, that's here. Then I'll plot 1/2, 1, so I go right a half and up 1. I go right a fourth and up 2, right an eighth and up 3. So you can see what's happening here. The graph is getting infinitely close to the y-axis, but going upward. Okay? Then if I plot 2, -1, that's down here, and then 4, -2, that's down here, and then 8, -3 is down here. The graph is flattening out in the downward direction. So this is the graph of y equals log base 1/2 of x. Now I need my transformations, so I'll start with my x transformations which happen inside the logarithm, inside the argument. So the x transformations, I take my x minus 3 like it's in an equation that I'm trying to solve for x, and figure out what I have to do to get x by itself, which in this case is add 3. And that is my x transformation. So add 3, and since it's an x transformation, I'll say 2x. My y transformations happen outside the log, which now I've got two of them, the negative and the plus 2. So my y transformations, I have to write them in order, the order that they happen. So I multiply the log by the negative first, and then I add the 2. So multiply by -1. And since it's a y transformation, I'll say multiply y by -1. And then I'll say add 2. Again, it's a y transformation, so I'll say to y. And I have to do those in that order. Okay? So now I just apply all three of these to my order pairs and my asymptote, and I'll get my new graph. I'm not going to do that in the interest of time, but you would of course add 3 to x. Maybe you'd put a plus 3 next to each of these. All that's going to do is move your graph to the right 3 units. I also have to add 3 here because this is an x. Okay, so make sure to add 3 to not just your x order pairs but your x equation as well. And so I'll get you started here. What's going to happen is roughly you're going to get these new order pairs, you'll get this new asymptote x equals 3. So your graph now is going to look something like this. So if this is 3, your asymptote's going to be here, and your whole graph's going to move right 3 and do this kind of thing. Still have the same shape. Get infinitely close to your asymptote, but move right 3 units. And then you're going to multiply your y's by -1. When you do that, your graph's going to flip over the x-axis. So your asymptote's not going to be affected because it's an x and y transformations don't affect it. But now your graph's going to get close to your asymptote on the bottom and flatten out on the top like this. And finally, adding 2 to y is going to move your entire graph up 2 units, which does not affect your asymptote again. So you still have the same asymptote at x equals 3, but now your graph, instead of going through this point, it's going to go through 2 points higher right here. So it's going to flatten out to the right and approach your asymptote, which is going to be raised up higher than it was before. And so roughly, if you work this out, you'll get this graph. Okay, you'll get more precise points, but that's the idea behind it. Okay, so that's how you graph logarithms using transformations. The parent function is your log of x. Make sure your base is included in there. And then your transformations, your x transformations happen inside the argument, which is what you're taking the log of, and your y transformations happen outside of the log. Okay, I hope this is helpful.